Russia. Spring, 1943. The thaw has begun. A Tiger I tank sits half-buried in the mud, its weight pressing deep into the soaked earth. Steam rises from the exhausts, mixing with the cold morning air. The engine rumbles, low, uneven, straining against forces it cannot overpower. Inside the hull, the driver tightens his grip on the control levers. Sweat beads beneath a steel helmet. He pushes forward. The Maybach engine roars louder. Treads claw at the ground but slip. Steel grinding against wet clay. A corporal drops into the mud behind the tank. Wrench in numb fingers. He pounds at a jammed access panel. Metal rings out, sharp and desperate. Another attempt. The transmission snarls, an awful mechanical screech that drowns out distant artillery. A sudden jolt. The tank shudders, then falls silent. The crew exchange glances in the dark. Not fear, frustration. Their machine, the one meant to dominate every battlefield it touched, is crippled without a shot being fired. This wasn't a rare moment. It was the beginning of a mystery no one yet fully understood. The Tiger I did not begin as a monster. It began as an argument. By 1937, German planners were already preparing for a war they expected would be decided by steel and shock. The Panzer Force needed a breakthrough weapon, something heavier, something that could lead assaults against fortified lines. But the debate inside the German army and industry was divided. Mobility and numbers, or invincibility and firepower? By 1941, that question was answered for them on the vast plains of the Soviet Union. Reports from the Eastern Front spoke of T-34s with sloped armor and KV-1s that German 37mm and even 50mm guns struggled to penetrate. Suddenly, light and medium tanks looked obsolete. Shock was now on the other side. The order was clear. A heavy tank must be rushed into production. The Tiger's design ambition, what rolled out of the factories in August 1942, was a machine meant to dominate every engagement it entered. 57 tons of steel, up to 120 mm of frontal armor. Ferretti. The fearsome 8.8 cm McKee 36 L56 gun derived from the legendary anti-aircraft cannon, a silhouette meant to intimidate. A drivetrain never designed for such weight to move this armored castle, engineers turned to Maybach, the longtime supplier of German tank engines. The HL-2I-10 and later HL-230 V12 engines were powerful, on paper. They produced over 600 horsepower, but pushing nearly 60 tons through difficult terrain tested the limits of every bolt and bearing. Power from the engine flowed into the Maybach, Olvar AK-7-200 pre-selector transmission, and finally into the final drives at the front of the tank. These components were precisely machined and complex, exactly the kind of engineering that hated mud, shock load, and neglect. Early prototypes had warned of trouble. Production pressures ignored those warnings. Rushed into war the Tiger, I first tasted combat at Leningrad, September 1942, under Schwer Panzerabteilung 502. The battlefield was a swamp of mud and shell holes, terrain ideal for revealing mechanical weaknesses. Two Tigers became bogged down and immobilized before reaching the front line. Soviet fire was not required. Gravity and mud were enough. Next deployment. Tunisia, early 1943, with Schwer Panzerabteilung 501. Heat, dust, and long supply lines created new torture tests for the drivetrain. Here, too, breakdowns outnumbered enemy kills. Some tanks were abandoned intact simply because repair was impossible under fire. By mid-1943, at Kursk, Tigers from 501, 502, and 503 battalions formed the spearhead of Operation Citadel. Their gun and armor dominated duels with Soviet armor. But even here, on their most famous battlefield, reports told the same story. The Tiger killed everything it hit. But it didn't always move when it needed to. The engineering trade-off German armored doctrine expected heavy tanks to operate in carefully coordinated, high-support, short-distance offensives. Tigers were never intended to drive dozens of kilometers per day. Their presence at the tip of German counterattacks forced them into roles far beyond design limits. The Wehrmacht wanted the overwhelming power of a fortress and the agility of a medium. Physics refused to compromise as production increased, 347 Tigers built in total. The brutal arithmetic of war pushed more vehicles to the front faster than Germany's shrinking industrial workforce could perfect them. Heat treatment of alloys, precision machining tolerances, and component quality control all began to vary. The result was predictable. Gear teeth chipped under stress, final drives overheated, transmissions seized under sudden torque. Codierde to fee, repairs consumed hours of labor, and difficult-to-obtain parts frontline crew reports repeatedly warned Berlin. If the engine survives, the transmission may kill us. For the men inside these machines, every attack carried a hidden gamble. Not enemy guns, but mechanical betrayal. And when the first operational losses of Tigers came not from enemy armor, but from internal failure, commanders demanded answers, because this wasn't a mere inconvenience. This was a problem that could change the war, if the Allies ever learned its truth. The first truly revealing clues came from the battlefield, not from wreckage, but from perfectly intact Tigers that simply stopped moving. When a tank worth a small fortune is abandoned without a fight, commanders take notice. Recovery crews took greater risks to tow Tigers considered dead, only to discover the same autopsy result again and again. The armor was untouched, the gun immaculate, the transmission broken. Field failure patterns. German maintenance logs from 1942-1943 describe recurring symptoms: grinding jumps during gear shifts, sudden loss of drive power, locked gear selector mechanisms, catastrophic failures in the final drives. One Tiger in Tunisia, with Schwere Panzerabteilung 501, was recorded as having 7 transmission replacements over just a few months of operations. Spare parts were scarce. Skilled mechanics were scarcer. Even worse, under battlefield stress, crews made mistakes. Improper shifting at high torque. Sudden direction changes. Clutch overuse in mud. Every error punished the tank more severely than any medium panzer. Behind the front lines, Tiger workshops turned into triage hospitals for crippled steel giants. Plenty of armor, but broken hearts. Captured without a shot. Allies didn't need to knock out Tigers to obtain them. They simply watched from a distance as German crews set scuttling charges and fled. Rather than be trapped with dead weight, the British seized their first relatively intact Tiger in early 1943 in Tunisia. Intelligence officers immediately recognized the opportunity. This was a technological goldmine delivered by mechanical failure. Soon after, more Tigers were recovered in the East. Each one offered precious insight into German engineering. But the biggest prize would come later in Italy, where a Tiger from Schwere Panzerabteilung 504 was captured in a condition perfect for study. It rolled onto ships and into secure workshops in Britain. Allied analysts believed they had already seen the best Germany could build. But inside the Tiger were questions far deeper than armor thickness and gun velocity. Why could the most feared tank in the world be humbled by a slight incline, a patch of mud, or a misjudged gear shift? British technical intelligence priorities. Britain's scientific war was systematic. Every enemy machine was documented, disassembled, tested to destruction aircraft, torpedoes, rockets. And now, Germany's heaviest armor. The Tiger's manufacturing precision impressed Allied engineers, but they also found surprising inconsistencies in steel quality, machining finish, and component durability. A single conclusion began to form. Power and protection had outgrown the mechanical systems beneath them. Yet hypotheses were not enough for war. They needed hard evidence, laboratory, metallurgical evidence, to understand failures, not just witness them. British metallurgists prepared their tools: cutting wheels, hardness testers, microscopes. They were about to peel open the Tiger's greatest secret, and the shocking truth inside those gears would change the reputation of German engineering forever. Angle 1. The human burden inside. A Tiger's hull, 5 men lived with the tension of invincibility and uncertainty. The driver, the most critical yet least visible, carried the responsibility of guiding 60 tons of steel across ground that actively resisted it. Training manuals stressed smooth operation, careful gear changes, steady torque. But combat rarely cooperated. Mud, fear, and sudden orders from the commander forced quick decisions that punished the transmission. Morale was a fragile alloy. Crews trusted their armor. They trusted their gun. But they did not always trust their mobility. Every rumble that sounded wrong, every stutter of the gearbox, planted a seed of dread. This could be the moment it stops. And in frontline combat, immobility was a death sentence. The Tiger gave its crew unmatched firepower, but it also made them captives of its own complexity. Angle 2, tactical reality. German doctrine envisioned Tigers as breakthrough weapons, measured thrusts into enemy defenses with strong logistical support. But war demanded more. As fronts collapsed, Tigers were sent to plug holes, race to emergencies, or retreat rapidly under pressure. Such missions forced excessive maneuvering, long marches, and sudden directional changes, each a mechanical stress test. The Tiger dominated when it fired. It suffered when it moved. When a Tiger stalled on exposed ground, enemy artillery shifted focus instantly. Its armor could resist many hits, but stationary targets could be isolated, encircled, and eventually neutralized. Commanders recognized the contradiction. Their strongest tactical asset could become their greatest liability if denied mobility for even a moment. Angle 3. Engineering and metallurgy. Tiger's drivetrain was a masterpiece of precision engineering, and a prisoner of it. The Maybach Olvar AK-7-200 transmission required exacting tolerances and pristine lubrication. Any contamination, mud, ice, dust, accelerated wear. Gear teeth endured massive torque spikes due to the tank's weight and abrupt terrain changes. Metallurgically, heat treatment inconsistencies in wartime steel could weaken components. Fatigue cracks formed where microstructures were overstressed. The final drives, mounted at the front to steer the tank, bore enormous loads. When they failed, movement ceased instantly. On paper, the Tiger was mechanically sound. On the battlefield, physics wrote harsher rules. Angle 4, leadership and doctrine. German high command believed the Tiger could shift the strategic balance, even in small numbers, so production was rushed. New battalions like 503 and 505 deployed Tigers before mechanics were fully trained or supply chains prepared. Commanders demanded offensive results, often ignoring engineering limits. The prestige of the Tiger became a trap. Losing one due to mechanical failure felt like an embarrassment, one that reports often softened or omitted entirely. Yet the failures mounted, quietly shaping operational outcomes. Leadership asked the Tiger to be unstoppable. Engineering asked for time. War gave neither. Multiple realities collided inside the Tiger's steel frame. Human stress, tactical urgency, scientific precision, and strategic ambition. To solve its mechanical mystery, all these angles would need to be understood together. Angle 5, enemy adaptation Soviet and British commanders quickly learned that a silent tiger was as valuable as a destroyed one. Crews abandoning intact vehicles due to mobility failures created rare intelligence prizes. In Tunisia, British troops approached a tiger cautiously, expecting booby traps or hidden gunners. Instead, they found pristine armor and an engine that refused to turn. More followed. On the Eastern Front, Soviet forces adapted tactics based on these discoveries. Anti-tank gunners were trained not only to penetrate, but to immobilize, aiming for tracks and final drives when penetration was unlikely. Once stuck, even a tiger became vulnerable to artillery, infantry, and demolitions. Enemy doctrine evolved. Force the tiger to move. The terrain will do the rest. Allied reconnaissance units also learned to track repair columns and recovery vehicles because where they gathered, tigers had broken down. Soon, frontline soldiers joked that the best anti-tank weapon was a swamp. The fearsome reputation of the tiger survived. But over time, so did a critical counter-narrative. If you could keep it moving, it would kill you. If you could stop it, nature would finish the job. Angle 6. Moral and logistical consequences. Every tiger produced drained resources that Germany increasingly lacked. Skilled labor, alloying elements, precision machining time. A single tiger could cost as much as 2 to 3 Panzer IVs, and maintaining one required a small army of mechanics and spare parts. Transport was an ordeal. Bridges collapsed under its weight. Rail cars needed modifications. Fuel consumption was punishing. From a moral standpoint, the tiger embodied a strategic gamble. Fewer machines of unparalleled power versus many machines of adequate strength. When one failed mechanically, the loss was doubly painful. It wasn't just combat power removed, it was a showcase of German technological prestige. Crews sometimes destroyed disabled tigers rather than risk them intact in enemy hands. But many were captured anyway, raising uncomfortable questions. Was it ethical, strategically, to pour irreplaceable metals and engineering talent into vehicles that defeated themselves? Allied engineers saw another angle: reverse engineering. Examining German steel composition, heat treatment, and machining techniques yielded insights that improved Allied armor development. The Tiger's transmission failures were not just a weakness. They became lessons. Germany's quest for battlefield dominance had furnished its enemies with a roadmap. The Tiger I was not merely a tank. It was a paradox, a triumph of design trapped inside the limits of wartime reality. And when British metallurgists finally placed fractured gears beneath their instruments, they were not just studying metal. They were uncovering the truth that would define the Tiger's legacy. A truth about how and why one of history's most feared weapons so often defeated itself. July 1943, Kursk, Operation Citadel. Schwere Panzerabteilung 505 pushed toward the village of Poniri, the Tiger battalions forming the tip of the assault. The thunder of their Maybach engines announced a threat no Soviet crew could ignore. Tigers advanced through wheat fields, their 8.8 cm guns punching through. Soviet armor at distances beyond retaliation. But the ground beneath them was unforgiving, cratered, softened, ready to betray them. During the approach to Hill 253-5, 3 Tigers halted almost simultaneously. No enemy fire had touched them. Drivers shouted over intercom wires. The diagnosis arrived quickly. Final drive jams, judged not repairable under fire. The spearhead paused. Momentum died. Soviet anti-tank crews exploited the delay, calling artillery that hammered the stranded vehicles until German engineers had no choice but to blow the Tigers where they sat. In the same operation, to the south near Prokhorovka, Tigers from Schwer Panzerabteilung 503 attempted rapid repositioning to counter a Soviet breakthrough. Hard turns under acceleration, exactly the situation final drives hated, led to grinding internal seizures. What should have been a crushing armored counterattack dissolved into immobile strongpoints, bypassed and isolated. By the end of Citadel, many Tigers were counted as losses without enemy penetrations. German commanders finally wrote the truth plainly. Mobility kills are as decisive as total destruction. The turning point of intelligence, while the battlefield revealed catastrophic symptoms, Britain soon acquired the most valuable clue yet: a Tiger's drivetrain with its failure fresh, intact, and identifiable. In May 1943, during the fighting around Jebel Jaffa in Tunisia, elements of the British 4th County of London Yeomanry found a Tiger from Schwer Panzerabteilung 501, abandoned after its transmission failed mid-withdrawal. The crew had left demolition charges, but rushed retreat meant they were never armed. The tank was captured mostly intact. The turret, armor, optics, radio, all impressive. But British intelligence eyes went immediately to the transmission bay. They wanted to see the part of the Tiger Germany didn't control perfectly. The AK-7-200 gearbox was removed, greased casings peeled back, fractured components marked and wrapped. The drivetrain, the heart of the mechanical mystery, was shipped to the UK via Bizerte. It arrived at Chertsey for preliminary inspection, then on to the Royal Armament Research and Development Establishment and associated metallurgical laboratories. German battlefield prestige was now laid bare under magnifying lamps. On one side of the war, Tigers were stalling at critical moments, reshaping battles that depended on speed and precision. On the other, British scientists prepared to cut into hardened steel, to measure its hardness, to study its microstructure, to gather the truth atom by atom. The saws were rigged, sections were marked. The first test cut was about to begin. The gearbox sat under bright lamps, drained of oil, its casing split like a cracked skull. British engineers, some veterans of pre-war racing transmissions, others pure laboratory minds, began with the simplest step, a visual examination. The failure surfaces weren't uniform. Instead of a clean overload shear, they saw beaches of granular texture spreading from darkened origins. That was the first hint. Fatigue, not battlefield stress alone. Next came hardness testing. Vickers indentations mapped a hardness gradient across failed teeth. Some values were significantly below expected specification for heavy-duty gear steels of the era. Inconsistent heat treatment, they noted. Either over-tempered, softening the metal, or inadequately quenched, leaving patches too brittle. Germany's late-war industrial strain could plausibly explain such variability. Bombed factories, rushed schedules, skilled labor scarcity. Where archival documentation is lacking, these remain evidence-supported hypotheses rather than absolute conclusions. Polished samples under light microscopy told a sharper story. A proper high-carbon steel gear tooth should reveal fine martensitic structure for shear resistance. Instead, sections revealed mixed bainite and ferrite, a sign of partial transformation, neither tough nor strong enough for repeated torque shocks. Microcracks spidered out from inclusions, tiny impurities, slag remnants from production shortcuts. Metallurgists logged each one. Every microscopic flaw represented a future breakdown on the battlefield. Then came fractography, using the period's optical methods. Beach marks, growth rings of tired metal, showed that cracks initiated at the root of the teeth, precisely where stress concentrates when a Tiger pivots hard or grinds through mud. Corrosion pits suggested contaminated lubricants, dust, moisture, and metallic debris circulating inside the transmission after earlier partial failures. Maintenance logs from recovered Tigers corroborated this. Crews often had to make do with insufficient filtration and hurried field servicing. Chemistry confirmed the final piece. The alloy composition hovered outside optimal ranges. Slight deviations in manganese and molybdenum, critical for strength and hardenability, hinted at resource dilution, again, a plausible wartime compromise rather than deliberate design flaw. One engineer summarized the finding in language later echoed in technical reports. This is not a single defect. It is a system strained to breaking. The conclusion was not that German engineers were incompetent. Their design ambitions, an 88mm gun on a moving fortress, pushed metallurgy to its edge. But design outpaced industrial reality. A drivetrain conceived in ideal conditions was forced into Russia's mud, Tunisia's heat, Kursk's brutality. Even the best trained drivers couldn't prevent what the steel itself foretold. When these technical results reached intelligence officers, the implications were decisive. The Tiger was lethally powerful when it moved, but its movement was never guaranteed. Each breakdown stranded a priceless machine and elite crew in enemy territory. The Bao myth of invincibility cracked along a microscopic fracture line, and as British analysts typed their final assessment, planners realized the truth. The Allied strategy didn't require destroying every Tiger. They only needed to make them drive. German frontline officers had sensed the truth long before engineers in London proved it. Reports from Schwer Panzerabteilung 502 near Leningrad in late 1942 recorded that nearly 50% of their Tigers were immobilized by mechanical issues at any given time. A commander from Espazabtet 501 in Tunisia noted that his unit entered battle with only 12-15 operational Tigers, despite having more on the rolls, because repairs lagged behind breakdowns. Figures based on wartime maintenance logs and post-war assessments. A Tiger could require 10+ hours of field maintenance for a single hour of combat driving. Final drive failures often stranded them beyond recovery, forcing demolition charges to prevent capture. In spring 1943, a German tactical bulletin acknowledged the limitation bluntly. Where the Tiger fights, it dominates. Where it must travel far, it disappears. Field Workshop Memorandum, Eastern Front. 1943, locally circulated report. Germany adapted doctrine around these constraints, shorter deployment distances to preserve. Transmissions, transport by rail whenever possible, Tiger spearheads. Only when terrain favored armor increased tow vehicles and maintenance. Columns attached to heavy units. The Tiger became less a roaming predator and more a localized ambush fortress. Meanwhile, Allied planners exploited the weakness. Intelligence briefs circulated among armored brigades advised force movement. The Tiger's strength is static. Its defeat lies in motion. British Tank Technical Intelligence Summary, 1944, phrased per surviving excerpts. Attrition followed a predictable pattern. Few Tigers died to gunfire. Many died under their own weight. Clutches burned out, gear teeth shorn, final drives fused. Each loss was strategically expensive, consuming scarce resources and elite crews. When the British metallurgical results came in, conclusions traveled fast, first as Army technical bulletins, then as updated unit tactics. Workshops were instructed to keep detailed logs of captured vehicle damage. Operational planners received guidance to avoid frontal duels and instead pressure mobility, funneling heavy German tanks into soft ground or forcing repeated repositioning. By late 1944, the Tiger was still feared, but no longer mythic. Its vulnerabilities had been documented, distributed, and weaponized. After the war, Allied and Soviet engineers dissected dozens of recovered Tigers. Their verdict shaped the future of armored warfare. Raw firepower and armor could not compensate for mechanical fragility. This lesson came to define NATO and Warsaw Pact design philosophy. Mobility. Overbuilt armor logistics capacity determines battlefield dominance. Maintenance doctrine must be engineered. Not improvised American thinking evolved from the wartime Sherman to the post-war Patton series, and later the M1 Abrams, tanks designed for high reliability and strategic mobility, with engines and transmissions optimized for modular servicing. British and French development similarly emphasized ease of maintenance, standardization, and large-scale sustainment. Even Germany's own Cold War designs, Leopard 1 and 2, represented a philosophical reversal. Lighter, agile, fully industrially supportable. Military historians came to cite the Tiger as a warning. A tank that cannot move is not a weapon. It is a bunker that cost too much. Reliability became an ethical consideration too. Sending crews into battle in vehicles known to fail under stress burdened leadership with moral responsibility. Post-war doctrine formalized the expectation that armored vehicles must be designed with the mechanic and the supply officer in mind, not only the gunner. In archives and museums, Tiger gearboxes remain artifacts of ambition and overreach. They reflect Germany's industrial overstretch, a nation trying to build superweapons while losing the factories and materials needed to sustain them. The metallurgists who peered through microscopes in 1944 could not know the long arc of their discovery. But their work became part of a fundamental truth in armored engineering. A tank is a machine first, a weapon second, and machines demand humility. Their findings shaped textbooks, procurement policies, and battlefield planning for decades. Every modern tank rolled from a factory floor carries this historical memory in its driveline steel. Strength must be balanced with support. Heroics must be balanced with realism. The Tiger's legacy is not merely that it was feared. It is that it broke, and the world learned why. Today, a Tiger stands silent behind ropes and polished concrete floors. Tourists circle it, admiring the thick plates and the long, predatory barrel of the 8.8 cm Couquet 36. Children press their palms to the glass, imagining unstoppable power. They do not hear what the old mechanics once heard: the harsh grind beneath the steel. In museum light, the flaws are invisible. The fractured teeth have been replaced. The gearbox is sealed. The scars are polished out. Only the weight remains. The weight that once defeated its own machinery. Somewhere in a dusty archive drawer lies a metallurgist's handwritten note. Heat affected zone. Hardness inconsistent. Failure by fatigue. Clinical words. Yet behind each line were exhausted crews, caught between an enemy in front and a machine failing beneath them. War does not forgive the imperfect. A tank like the Tiger promised certainty, invincibility, dominance, fear in the hearts of foes. But war is a realm of logistics, grit, and material truth. The strongest armor cannot protect against the consequences of industrial strain or strategic overconfidence. Even giants collapse if their foundations crack. The Tiger's story reminds us that weapons are not just engineered. They are endured. Every decision in metal echoes through human lives. Every shortcut, taken in a furnace or factory, becomes a future battlefield risk. The rusting Tiger, still as a monument, holds one final lesson beneath its broken gears. Power means nothing if it cannot move forward.